Welcome to the second part of the Dynamic of Structure lecture. So far we have found the solution of a dynamic system with 1 degree of freedom. But of course the structures have many degrees of freedom. If the structure is a continuum, it's going to have infinite degrees of freedom. But if we represent the structure as finite element mesh, then it's going to have finite degrees of freedom. So let's go to the equations, the dynamic equations in the finite element formulation. So we have here the balance equations, the second Newton law for a infinitesimal element. So mass multiplied by accelerations is equal to the force due by the stresses plus the force due to the body forces. So U is the displacement of the structure, that is a vector. So as before, to get the finite element formulations, we need to multiply by the virtual displacement and integrate over the volume of the structure, the volume of the domain. This is the weak form. Then we have to integrate by parts, and we obtain these two terms from this term. So this is the virtual work done by the internal stresses, and this is the virtual work done by the tractions over the area of the domain. Then we introduce the interpolation functions, or in general the shape functions that connect the displacement in every point of the domain with the nodal displacements. If we replace these expressions into the weak form, then we obtain this one, these equations. Notice that in these equations I didn't consider damping, just to make the equations a bit simple, but it is possible to include the damping with no problem. So in this case I am introducing just the mass times accelerations, the inertia, and the external force. So the external force, let's go where the external force is. So the external force is going to appear here. So is the external body force. Here I have another external force that can be attractions, a force acting on the boundary of the domain, like the wind is acting on the boundary. So these two terms is the sum of the body forces and the boundary forces. Here I have a new term that is the mass matrix. Rho is the density of the material, and as always I have the stiffness matrix. So these equations reduce to the static equations if the accelerations, the second derivative of the nodal displacements, is 0. So these equations can be solved very simple. So we just need to introduce the nodal velocity as the derivative of the nodal displacements, and the variation of the nodal velocity can be calculated from these equations as these expressions. So you can integrate this by step, as we did with the transient dynamic thermal solver, and we are going to need some boundary conditions. We will need the displacements and the velocities at time equal to 0. So notice that in this case I need to calculate the stiffness matrix anytime. Yes, anytime if the mesh is changing. We need to do some calculations in every time step. So this is the transient dynamic solvers. So the step-by-step solutions over all the degrees of freedom of the systems. So these solutions is computationally very, very expensive. So this is a transient dynamic solver. Since this transient dynamic solvers evolves with too many degrees of freedom, all the degrees of freedom of the structure, So it's computationally very expensive. And I want to introduce another solver that works with much less degrees of freedom. The degrees of freedom in this solver are the fundamental modes of vibration of this structure. So let's introduce the spectral response solver. The steps of this spectral response solver is first to find the vibrational modes of the structures. Then express the solutions as combinations of the vibrational modes, and then solve the response to each mode to an external actions that can be an earthquake, a wind load, a pedestrian load, etc. And then we superpose the response of all modes, and we have the spectral response solution. So let's start from the first point, how to find the vibrational modes of the structure. So I have here a video that shows the fundamental mode of a high-rise building, and this mode is activated by an earthquake. So there is an earthquake, and if you look at the background, the building is swaying, is oscillating. And you can see that the oscillations is around 6 seconds. This is the fundamental mode of vibration of the structure. So we are going to find the fundamental modes and the corresponding frequencies. So let's start from our equation, and we are going to assume that there is no forces. So the system is going to oscillate due to the initial conditions. So this is going to be our global matrix equation, and the proposed solutions can be given in terms of exponential. J is the imaginary number, square root of -1. And we assume that U naught is a vector, W is a certain frequency. So this is the solution that I propose for these equations. I just put the solution into these equations, and I get this equation that is a matrix equations. I wanted to obtain U naught, and I wanted to obtain the frequencies. So I have these equations, and these equations will have a non-trivial solutions, U naught different to 0, if the determinant of this matrix is equal to 0. So these equations give me a characteristic equation that is a polynomial. This is going to give me a certain number of natural frequencies that is equal to the number of degrees of freedom. So there is some more properties. So after you find each frequency, you can replace the frequency into these equations, and you can find the corresponding vibrational modes. And some mathematical properties of these vibrational modes is that they are orthogonal. What does it mean? Is that they satisfy this property. So it's like a dot products between the vibrational modes are orthogonal with respect to the mass matrix and orthogonal with respect to the stiffness matrix. These properties are going to be very useful in the derivation of the spectral response solver. These vibrational modes can be normalized. So this is the norm of this vector. It's going to be equal to 1. So this is the vibrational modes of the structures. The natural frequency solver is going to give me the natural frequencies of the structure and the corresponding modes of vibrations of this structure. Until now we have the fundamental frequencies and the vibrational modes of the structure obtained from the natural frequency solver. The next step in the spectral response solver is to express the solution that we are looking as a linear combinations of vibrational modes. So what we are doing here, so we are going to write our problem or equations like this. So this is the external force is written in terms of the mass matrix, the imposed accelerations, and here I am introducing the influence coefficient vector. This is a vector with n values. N is the number of degrees of freedom, and the value of this vector, the component of this vector is going to be 1 if the force is acting on these degrees of freedom, or 0 otherwise. So g is the ground accelerations, or the imposed acceleration in the system. So I'm going to assume that the solution that I'm looking for is a linear combinations of the vibrational modes. So I sum over all the modes, that is equal to the number of degrees of freedom, and I'm going to assume that the coefficients here are time dependent. So this is my proposed solutions, and I need to plug it here in my equation. So I get this equation that I can simplify by multiplying by one of the modes, the I mode transpose. I multiply this by these equations, and due to the orthogonality properties, this is reduced to n equations, where n is the degrees of freedom. So this is an equations. I'm going to divide all this equation by this quantity, that is just a number for each mode. And then after dividing by this, I'm going to get this equation, where what is this and what is this. So this is going to be, I'm not going to show this, but this is going to be the natural frequency of the I mode. And this quantity is the mass participations that is going to be given by this expression. And it's possible to show that the sum of all the mass participation is going to be to the absolute value of the module of the influence vector. So notice that now the solutions consist in solve this equation, that is the harmonic oscillations equation for each fundamental mode, and we already know how to solve this equation. So the next step is to solve the response to each mode to the external action. So we are going to assume that the external actions, as just an example, is earthquakes. So this is a typical acceleration versus time due to earthquakes. These accelerations act on the ground, but since the building is connected to the ground, it's going to act on the nodes connecting nodes of the building connected to the ground. So the ordinary differential equation that I have to solve is this one, where this is the gravity. So the solution is already given. We solved this already. It's the Duhamel solution that is simplified here because I didn't put damping. And I'm going to introduce a quantity that is the peak acceleration response. The peak acceleration response is the second derivative of this quantity, and I take the second derivative and I calculate the maximal value of the second derivative. Let's see how does it looks like. So if I solve these equations and calculate the acceleration response, I can calculate this as a function of the frequency, or I can calculate as a function of the period. The period is 2 pi divided by the frequency. So I am plotting here against the period for this particular acceleration. So you can see that the response is very small if the period is larger than 1 second. This is the natural period of this corresponding mode. But if the modes are around 0.3, 0.5, the response is going to be maximal. And if the frequencies are small, the response is going to be small. So if the periods are small, the acceleration response is going to be small, but it kinds of increase linearly. And this solution is with no damping, but I can extend the solution for different damping ratios, and the response is going to decrease if the damping increase. So I can calculate this spectral response against period given any acceleration versus time. This is going to be very useful. And for earthquakes, so the response is average over many earthquakes and is simplified by these expressions. So here it is assuming that the response decrease with the period. Here it is assumed that for small periods the response will increase linearly, and it is assumed that it's a minimal and maximal period where the response is approximately the same. So this is an approximation to these expressions, average over many earthquakes. So this is the spectral response in vibrational mode as a function of the period of the mode for an earthquakes. But we can do the same for any kind of time-dependent load. Apart from earthquakes, an interesting case is this effect of the pedestrians in the dynamic response of a bridge. So this is the Millennium Bridge that was inaugurated this millennium. And there, in the inauguration, there were a lot of pedestrians. The acceleration versus time produced by the pedestrians is given by this plot. So you can see that there are peaks that are kind of periodic, and the periodicity depends on the pedestrian pace. So you can see that due to the pedestrian pace, the bridge is going to start to oscillate at a similar frequency. This is a typical case of resonance. Luckily, this bridge didn't collapse, but after the inaugurations, so the engineers have to put some dampers to reduce the response to this particular frequency in the bridge. So you can see here that even the effect of the pedestrian, the dynamic effect of the pedestrian has a strong effect in the dynamic response of a bridge, and it needs to be taken into account. So now we go to the last part of the spectral response solver, that is the superposition of the response of all modes to get the total response. So this is our equations that we are trying to solve. So the spectral solution is given by this one. So this is the linear combinations over all the vibrational modes, and this is given by the mass participations over the response, spectral response, and the mass participation is in terms of the mass matrix, the vibrational modes, and the influence factor. So this quantity is the integral over the accelerations, imposed accelerations in the structure. This is the Duhamel solutions. So this is the spectral response, but we can do some simplifications because we don't want to integrate this over all the modes of the structures. It's going to be too complicated, too computational expensive. So one approximation is used to just to use the peak response. So in particular, the peak acceleration response is given by is assuming to be a linear combination of the response of all fundamental modes, where this is the peak acceleration response. So you can combine this like this or like this. There's two different ways to estimate the maximal response of the structure. So this is the, as we say, this is the acceleration response that can be plotted in terms of the period. The period is 2 times over the frequency. So in this way, so we don't need to know the details of the response. In these approximations, we only need to find the spectral response as a function of the period that is given in many cases. So, but in this approach, we only get the maximal acceleration response of the structure. But there is a way to get the maximal velocity response or maximal displacement response of the structure from these quantities. Is given in terms of the frequencies, so it can be calculated. Yes, so the spectral response solver use this quantity as an input. So you need to specify where the acceleration is acting. So the strand 7 is going to calculate the R matrix, and then strand 7 is going to calculate the mass participation factors or the peak response of the structure. So you don't need to specify the acceleration versus time. You need to specify the spectral response as a function of the period. So you don't need to include all the modes in this sum. So you only need to see which mode have influence in the response. Notice, so usually in strand 7, the frequencies are organized. All the vibrational modes are sorted according to the period. And if the period is too large, and this is the spectral response, very high periods, they are going to have very low influence. So you can reduce this sum to the first periods of the vibrational modes. But you have to check that this approximation is reasonable by calculating the total mass participations. That should be approximately equal to 80%. So the total mass participation is the sum of the mass participations. So if you include all the frequencies, it's going to be 100%. But since this is the case with the period, you don't need to include high periods in the calculation of the spectral response. So this is the end of the spectral response solver.